anyway. And I'll share my screen. Okay. Can you see my screen?
Yes, ma'am.
Okay. So, so do you know that there is this question answer?
Yes, I know.
Huh.
I see
So
that.
yes. So, 1 second. Yes. So in this here, um, so the formula of covariance, which is when you sum the differences, so x minus x bar into y minus y bar. So just like the formula for your sample variance has one, it has n minus 1 as the denominator. Just like that, covariance also has n minus 1 as the denominator.
Okay.
So in this question, when you are directly doing, if you would directly do covariance is going to solve based on um, like the denominator it will take is n. So what you need to do is whatever answer you get, you have to multiply that by n and then divide by n minus 1. So that effectively your
Okay.
denominator is n minus 1 now.
Okay.
Right? So for example, um yeah, I'm not sure what n, yeah, I mean yes. So it's just that this answer you have to multiply by n. So whatever is the length of this thing. So you can do a length x or length y argument. And then what you can do is, so that whole thing divided by, sorry, that whole thing multiplied by the length divided by that length minus 1.
Okay.
Yep. So yeah, so
Thank
this
you.
is like a trick question.
Okay,
So,
yes. So actually, I thought that they actually have four variants, no? And they form and they give the formula in question. So actually I thought that was the formula because in statistics means I am also means I am actually graduate from a statistics means
uh-huh.
degree. So in that actually I use formula this 1 by n formula actually I use that time in statistics lectures.
um, but
मतलब
I
ओके
but I understand that here they also say 1 minus n.
हाँ हाँ
Yeah. Um.
एंड जब मत हाँ एक्चुअली
Mm-hmm.
जब मैं मतलब मैं बैचलर्स में था स्टैटिस्टिक्स में तब हम लोग कोविडेंस था उसमें मतलब रिग्रेशन वगैरह था तो
Right,
उसमें
right.
एक्चुअली हम यही फॉर्मूला यूज करते थे सो मतलब यही सेम फॉर्मूला यूज करते थे सो मैं ये सोचा कि भाई ये फॉर्मूला से तो मतलब एक
Mhm.
करेक्ट लग रहा है आंसर तो वो रॉन्ग क्यों दिया तो उसके लिए मैं वो डाउट था
Right,
तो
right.
थैंक यू मैम
Yeah.
थैंक यू सो
Okay,
मच
okay. Just yeah, isko just keep in mind for your for the exam. If
okay yes sir.
yeah.
And ma'am there is a one question about the exam also
Mm-hmm.
hello
Yes.
मैम अभी जब जैसे अभी हम वैसे असाइनमेंट सॉल्व करते हैं तो
Mm-hmm.
हम ये जो असाइनमेंट सॉल्व करते हैं अभी हम कुछ कुछ जो कोर्स है वो आंसर वो हम आर में एग्जीक्यूट भी करते हैं
Right.
और उसके आंसर्स फाइंड करते हैं
हाँ.
सो अभी एग्जाम के टाइम जब हमारा जब ये होगा जब एग्जाम तभी हमें ऐसा सॉफ्टवेयर वगैरह कुछ करने को मिलेगा एग्जीक्यूट की फिर कैसे मतलब वो होगा
नहीं, सो जो एग्जाम में जो क्वेश्चंस आएंगे उनमें आपको सॉफ्टवेयर की जरूरत नहीं पड़ेगी. द क्वेश्चंस विल नॉट रिक्वायर यू टू डू एनी डिफिकल्ट कैलकुलेशंस. Like questions like this will not be a part of the exam. Okay, but maybe questions like this can come in the exam where you don't need R.
ओके ठीक ओके
Yeah, but also
थैंक
some questions can come which are based on like some formulas of R. Like you will see in assignment 9, which you'll see today. So there are some questions, like I just have some sample questions for you, which we'll discuss today anyway, but it'll be like this. So the question is, how do you calculate this in R? So you'll have four options of the command. Maybe you'll have to choose one of those as the answer. बट आपको आर सॉफ्टवेयर की जरूरत नहीं पड़ेगी. आर सॉफ्टवेयर के बेसिस पे यू कैन सॉल्व इट, बट
ओके
यू डोंट नीड आर.
ओके थैंक
ठीक.
यू सो
यस.
मच
ओके. Hi everybody. Any other question before we start today's session? Okay. Then I'll start the session. Give me just 1 second. Okay, the recording is on. All right. Oops. Okay. My screen should be visible now. So, welcome to the ninth live problem solving session for the NPTEL course Essentials of Data Science with R Software Part 1, where we are discussing a lot of things around probability and statistical inference. So, in starting from, so up until now, we have been talking a lot about probability. Starting from today's session, or rather starting from week 9, we are slightly being introduced towards statistical inference also, and that's what we will do in the upcoming 3 weeks as well. So far we have had these, everything's being recorded. You can take a look at the previous recordings. Everything we're discussing is getting uploaded on the Google Drive, and definitely make use of the discussion forum, because a lot of times if there are some questions where the answers might be wrong, or if there's some typo, so it's nice to know already that if somebody else is also having similar problems. Okay. So in this week, so there are two parts to this week's contents. So the first thing is something around bivariate normal distribution and bivariate and multivariate. And then we go on to something called the statistic, which we will see in in a few minutes. Okay, so starting off with the bivariate or the multivariate normal distribution. So this first formula that you see here is our familiar normal distribution formula. And remember, we attribute, or rather we call the normal distribution based on two parameters, right? One of them is this mu, that's the mean, and the other thing is sigma or sigma square. So where sigma is the standard deviation and sigma square is the variance. Okay. Now there is just one variable here. So the output here, so this fx function, the PDF here, that is based on just one variable. Everything else is known for a particular distribution. But now if we extend to two variables, so you can call them x1, x2, you can call them x and y. So it's absolutely up to you. But generally when there are just two variables, we call them x and y. But if suppose there were 10 variables or 20 variables or 100 variables, then generally they are referred as x1, x2, x3, and so on. So now this formula, it becomes slightly different. It's definitely, it looks a little more complicated. So here what you can see is you still have this minus sign. So this is exponent, right? So it's e to the power whatever is inside the bracket. Now here it was minus, and then the numerator here was x minus its mean and whole square. So here you can still see that it's there, x minus mu x square, y minus mu y square. And there is another term here. So generally when you're dealing with whole squares, you generally have this, so a square plus b square minus 2ab sort of a thing. So that is there here. So 2 and then this thing. And there is another factor here, which is rho. And if you remember from the previous week, this rho is actually the correlation coefficient, the Pearson's correlation coefficient. And we'll come to that in a minute. And the denominators here are their respective variances. Okay, so sigma x square, sigma y square, and this is sigma x, sigma y. And there is, in addition to this two, there is another term which also has that rho here. So 1 minus rho whole square. And the outside here is also a little bit more complicated. Now you don't have root over 2 pi. You just have 2 pi because it's now squared up, sort of. Instead of sigma, you have sigma x, sigma y. And then again, you have 1 minus rho square and whole root of that. Now, so variances, right? So these are always positive. We've seen earlier variances are we variances, or rather even standard deviation. They're all we always take the positive value, but the Pearson's correlation coefficient, that is that is always between -1 and 1. So between -1 and 0, it indicates that they have a negative correlation. So when one increases, the other decreases. And if they have a positive correlation, which is between 0 and 1, then they have a so one increases, the other also increases. So if you see a formula which is in this form, then based on these, what is there in the numerator and what is there in the denominator, you can identify what is the value of mu and sigma respectively. And there are a few questions like that in this week's assignment. Okay. We'll also take a few examples. Another thing is, so of course, this is there. Now you can imagine if there were three variables, it's going to become very, very complicated, right? So rather than writing the whole thing down, what you basically want to write is you want to write these parameters. Everything else is in some sort of a pattern. But the two parameters that you need to write, again, there is mu, but rather than mu, just a single mu, it's a vector mu. So for example, if there are p random variables that we're talking about, so you can call them x1, x2, x3 up until xp. So all of these are the respective means. We just denote it in one column, okay, because it's vertical, so we'll just call it a column vector. That's just how it's denoted. And this thing, the other thing, we call it sigma. So this is actually capital sigma, and this sigma is like lowercase and uppercase sigma. So this sigma, the capital sigma, that's actually a matrix. We have seen a part of this in the last week where we are calling it the matrix, the covariance matrix. So this is a square matrix with dimensions p and p, so p rows and p columns. And um, so what you can see here is all the diagonal elements. Okay. So all the diagonal elements, which are 1, 1, 2, 2, 3, 3, these are actually your um, variances. Okay. So variance of the first variable, second variable, so on and so forth, and the pth variable. And all the non-diagonal elements, they are your covariances. So if you just focus on this part, if you just take a look at this thing, so what you can see is, so that's your covariance of x, that's your covariance of y. Oh, sorry, variance of x, variance of y. And the other two things, even though you're writing it as sigma 1, 2 and sigma 2, 1, they are the same thing, and that's the covariance of x, y. And then, can one of you tell me what is the formula of correlation, covariance, variance? How are they related?
Correlation is a ratio of covariance divided by standard deviation of x into standard deviation of y.
Yes, perfect. So yeah, so based on this 2 by 2 matrix, you can calculate what is rho, and that can be plugged in. Again, it's complicated, but this is how it can be done. Okay. Then, just like we had seen last time for some bivariate distributions, that you can calculate marginal probabilities and conditional probabilities. Again, for these, for normal distribution, it can become very complicated. So we will not go into too much detail of how it can be solved and like that. But just for simplicity, so if we want to calculate the marginal probability of x, that means y is known to us. So then y goes out of the equation and it becomes a simple normal, like a usual univariate normal distribution in x. And likewise, the one in y becomes a simple one in y with the same mean and the same standard deviation and the same variance. So no difference at all. Okay. So that's like a unique property of normal distribution, that it no longer just depends on y. Everything else stays the same. Then the other thing for which is for conditional probabilities. So here what's happening is that y, when a certain value of x is given to you. So imagine this is that fixed value of x. So even though we are writing x here, but this is actually a fixed value. fixed or known value rather, right? Which you can just plug in based on what is given in the question. So then this sort of a thing is, it's only going to be in terms of y, right? So you will have mu y and sigma y and yeah, mu y, sigma y, and obviously the rho will anyway be used. So now that also becomes, this is also a normal distribution, but now there is a new mean and a new variance. Okay. So this whole thing is the new mean. A single, the by, it's like a univariate normal distribution, but that univariate normal distribution has a new mean and a new variance. Does this sort of make sense? Yeah.
Yes, ma'am.
Okay, great. Thanks. Okay. So mostly what you need to sort of remember from these couple of slides is how the thing looks. So what is the general pattern? If you can remember these, it will be really great. But at least try to remember the overall pattern, if not the exact thing. Okay. All right. So that's the first part. And of course, we'll see some questions and we'll also take a look at this in R. But after this, we are going to go into something called sampling distributions. And again, it will be discussed more in the next few lectures. But this is like a introduction to that. Okay. So now, so we had seen earlier some cases where, let's say you have a random variable x, and then you are doing some manipulation on that. Maybe you're squaring it up, maybe you're dividing it by something, maybe you are multiplying it by something. So let's say you had random variable x, it had mean mu, variance sigma square, and then you multiplied it by a, right? So if you multiplied it by a, your new mean became a times the original mean, and your variance became a square times the original variance. Remember, this is what we had done. So what that was basically a function of that random variable. Okay. Likewise, so what we'll call as statistic, and we'll denote it with the small t, that is also a function of the original random variable. So that is also a random variable. This is how we denote it. It's just complicated looking, but these statistics, the t, this could be sum of random variables. That could be, you take the minimum of them, maximum, mean, variance, z value, anything. Okay. So some of them take two random variables, some of them can take more random variables. Mostly we will work with two or three random variables, not more. But these can take any number of random variables. Okay. So now um these statistics, they will have a probability distribution because they are a random variable. They'll follow some pattern. Okay. We will call them sampling distributions. The pattern, the probability distribution is going to be called sampling distributions. It's just how they are named. That's it. Because they are used for samples. Remember, we talked about population and sample, right? So since these statistics, the distributions of these statistics are used when you have a sample, so that's why they're called sampling distributions. And in addition to the parameters of mu and sigma, or mu and sigma square, they also have another parameter called degrees of freedom. We'll talk about that also. And the three of the most common distributions are chi-square distribution, which is denoted by this Greek symbol chi. It's like a fancy X. It's called chi-square. And then you have a t distribution, and then there is an f distribution. Okay, so we'll talk about this now. So just to let you know, I have two slides for each of these patterns, each of these distributions, and they're roughly in the same, roughly similarly designed slides. So it's for your reference. So definitely, take a look at this even after the class, or like if you've registered for the exam, then definitely take a look at this before that. Okay. So when is a certain random variable following chi-square distribution? So we start off with a standard normal distribution. Okay. So for n independent random variables, so again, remember here it said we could take any number that could be 1, 2, 3, whatever. So for n random variables, which all of them, they're all standard normal distributions. So all of them have their mean 0. All of them have their variance and standard deviation 1. We take the sum of their squares. Okay. So they're standard normals. So we can denote them with a z. Remember, z is how we made something standard normal. And this is already standard normal. So we'll just say, so sum of their squares, that has a chi-square distribution with n degrees of freedom. Now, what is n here mainly? We'll come to it in a minute. If instead of taking standard normal distributions, if you would have taken just normal distributions, which have mu and sigma square, then you don't take a sum of their squares directly, but you take a sum of their z values. Again, doing the same thing. Okay. That also has n degrees of freedom. This also has n degrees of freedom. It's just we are calling it central chi-square because you've now centralized these values, but that's not important. So now what's going to happen here is think about it. So for example, if this is your standard normal or normal distribution, okay, now you have many which are exactly the same. So imagine they're all one on top of each other, right? And if you sum them up, you're summing the squares. So it's going to look something like this. It's going to follow some sort of a similar pattern, but it's going to be taller. Depending on how many you add, it can become really tall, right? So, so now originally, so in all other distributions that we have seen so far, normal distribution, exponential, Poisson, none of them depend on n. None of them depend on how many variables you are dealing with. But in chi-square distribution, since it is, you are, this is summing up some existing random variables. So n is important here. Whether you are summing up 5 or whether you're summing up 10 of them, the height is going to change here. So of course, the area under the curve is always going to remain 1. That is true, right? But the nature of the graph also changes a bit, and we'll see some examples. So, so that's why that n, the value n here, how many random variables are you starting with, that becomes important. Okay, so that number is referred to as the third parameter. I mean, here actually the only parameter that you're looking at is n. Now you're no longer interested in what was mu, what was sigma, because you've taken the z variable. You've already centralized it. So the only parameter that chi-square depends on is n. Now you can define a PMF for this. Okay. Now you can see there is a, so it's very complicated, of course. Of course, there's x and its exponent, there's exponent of something, and there is this new symbol here. It's called the gamma function. We are not going to go into that at all. The only few things you can remember about the chi-square distribution is, of course, it is dependent on n. So it has n degrees of freedom. So you can see everywhere in the formula, the only parameter that you have is n. Now, PMF of this says that at x greater than 0, you have this thing, and then everything else is 0. So as such, this graph is not going to be correct because you remember the normal distribution, like your standard normal distribution was around 0. Now you're squaring everything up. So everything that was on the left side also goes to the right side, right? And it gets squared up. Oh, yes. No, actually, so this is it's actually a discrete random variable, right? Because you can only have 1, 2, 3, 4 based on n. I mean, I understand since it's coming from normal distributions, um, it becomes a continuous variable, but chi-square by itself, I think I would call it a PMF rather than a PDF, but it's actually a good point. Um, Let me double check and get back to you.
Yes, ma'am, because values of n are integer. It is
Yes,
not necessary that sum of square should be integer.
yes, yes, yes.
Definitely, they are positive, but
Yeah.
it is not necessary that they are integer values.
No, that I understand. But the inputs, so like n can only take up um natural numbers or whole numbers, right? 0, 1, 2, 3, 4, like that.
Yeah, that's true.
Right? So but
But
anyway, it's
PDF
still a fair
format
point.
has
Mhm. Okay. Yeah, good point. So okay, anyway, we'll come back to it. Maybe it should be PDF. Yeah, because X can have any value, right? Yeah, true. Hmm. Yes, I think so. Forget what I said. Yes, X can have any value, so it's going to be a PDF. You're right. Okay. And then the expectation and the variance. Now, after everything that's happened here, the expectation and variance are simply dependent on n. So always remember this parameter, whatever we are using in the formula, is what your expectation and variance are also going to depend on. When this formula had mu and sigma, then expectation and variance also had mu and sigma. When this formula had something like lambda, then expectation and variance were also in terms of lambda. Now, since this formula just has n, so expectation and variance are also n and 2. All right. Some properties of chi-square distribution. Again, we'll take a look at that in more detail in R in a few minutes. So it's non-symmetric. So what I've drawn here is not going to be, is not correct, but it's just for your, just for like a vague idea. It's always greater than 0 because since you're squaring up something and then adding, it's always going to be on the right side, not like no negative values. Shape depends on n, which is the degree of freedom. So at n greater than 5, the nature of the curve changes. Again, we'll see some examples. If you take two chi-square distributions, so one of them has n degrees of freedom, the other has m degrees of freedom, then their sum also follows chi-square distribution with simply n plus m degrees of freedom. Okay. Um, yes. Now you remember this thing we were just talking about this very briefly at the beginning of today's class with respect to a question from week 8 assignment. Um, so it's not exactly that, but you remember that sigma has 1 divided by n minus 1. So this is the denominator for sigma, and S, which is your sample variance, or yeah, I should say, yeah, this thing. So uh, this actually has n as the denominator. This is just for your, this is how it is. So if you multiply s square with n minus 1 and divide it by sigma square, then this thing that follows a chi-square distribution with degrees of freedom n minus 1. So this is something which, as far as I remember, there is a question like this in your assignment, and we will also solve a very similar question today. Okay, so that should give you an idea. Another thing which this last point is going to come more in use in the upcoming lectures. But so remember this sort of a notation. So again, instead of this value, for example, if it was any fixed value, A, B, C, D, whatever. So typically this is the opposite of CDF, right? CDF is generally from the lowest possible value up until that value that you're looking at. So whether it's minus infinity to A or it's 0 to A, whatever it takes, it's up to a certain value. For chi-square F and T distributions, sometimes we would be interested in looking at values above a certain value. So what's the integration? What's the area under the curve from here to infinity? And again, remember last time, I think this was last lecture or the lecture before that, we talked about alpha, two tail, one tail, tail on the left, tail on the right, both tails. I think it was last lecture when we discussed a little bit about normal distribution. So alpha does not really have a fixed position or value. Alpha generally depends on some part of the curve that we are looking at. Okay, so don't get confused that alpha is being used in different contexts every time. Again, this will come handy. I mean, this will come into the picture much more, I think, in the next lecture. But yeah, so just remember that when you're looking at a part of the curve, part of the area under the curve, then very often we refer to it as alpha. Okay, anyway, so that's some properties of chi-square distribution. So mainly what we did was, if you have standard normal distributions and you're summing up their squares, then the resulting random variable has chi-square distribution and it has n degrees of freedom. Now, if you take a standard normal variable and you take a chi-square distribution which has n degrees of freedom, and you have this sort of a algebraic equation. So you divide the standard normal by the root of chi-square by n, where n is the degrees of freedom. So again, remember how we defined a statistic? Statistic is a function of the random variable. It could be any function, sum, square, mean, whatever. So here what we did was we summed up the squares. Now what we are doing, we are dividing one by the other. So it's all of these are just mathematical operations done. So this resulting random variable, it follows t distribution or student's t distribution, and that also has n degrees of freedom. And we refer to it as t with n as the parameter. And I think this should also be called PDF then. It's definitely called PDF. So again, here you can see very, very complicated. But the thing to note here is that this is going to be the only parameter here is n. There's also this gamma function here, again, which we are not going into it. But the other thing is, this is now going to be, the range is entire minus infinity to infinity. The expectation is 0, so it's centered around 0. And the variance is n divided by n minus 1. All right. Yes, so that's that. So this is a symmetric distribution and looks like a normal distribution. In fact, it would look like a standard normal distribution because it's centered around 0, but it has thicker tails. So for example, suppose if this is your normal distribution, then for t distribution, if I'm drawing with blue, this is, oops, sorry. This is what it's going to look like. So remember, area under the curve has to be 1. Okay. So it could not be that this is taller also and thicker also. Area under the curve is going to be 1. So the t distribution has thicker tails. So the ends are thicker, which also means that now the variance is large, right? It's distributed over a longer area. And what happens is the shape depends on n. Of course, it's going to be slightly different every time because That's where it is. So that's even applicable for chi-square distribution. It depends on n. Shape depends on n. And here also the shape depends on n. But what happens is when you have a lot of, when this n here, when this n is really large, 30 or more, then chi-square and normal distribution almost become the same. So as n increases, this actually starts going up. So you can imagine this is going up, and then these are getting shorter and shorter, right? As n increases. So at n greater than 30, the blue and the red lines would almost become similar. Now here what we had seen, when you take sample variance and population variance, sample variance and population variance are related using chi-square distribution, where the degrees of freedom is n minus 1. Now, sample variance and population mean, okay, uh, different things. Sample variance, population mean, they are related using t distribution, also with degree of freedom n minus 1. And actually, this thing here is actually your sample mean. So you have sample mean, population mean, sample variance, and this is root n. This distribution follows this sort of a random variable, it follows t distribution. Again, here also, greater than a certain value, that's denoted as alpha. Again, this is going to come into the picture in next week. Okay, so we are done with chi-square distribution. We also talked about t distribution. The next thing we talk about is F distribution. So we started off with chi-square, where we are just taking standard normals. Then we talked about t distribution, where we are taking one standard normal and one chi-square. Now we are talking about two chi-square distributions. One of them, we'll just call them x and y, which have different degrees of freedom. So now x over m, so x divided by its respective degree of freedom, divided by y divided by its degree of freedom, follows F distribution. And now F distribution has 2 degrees of freedom, because you start off with 2 different degrees of freedom and you denote it with F and m comma n. Now there are 2 parameters. This also only is valid at x greater than 0. So I think here as well, we have to call it PDF. And yeah, so this is also always greater than 0. You have 2 values here. Again, absolutely, you don't need to remember this formula. Just remember that there are 2 parameters here. When this is solved and when the expectation and variance come into the picture, you can see that there are these denominators here. So x has a denominator x minus n minus 2, and variance has the denominator yeah, n minus 2, n minus 4. So based on this, we can say that n has to be greater than 4, because otherwise it's going to become 0, right? So we can't have, I mean, not 0. This would become like, this value would become 0 and the whole thing is going to become infinite, right? That can't happen. So n has to be greater than 4 for this. That's the restriction we have for F distribution. The 2 random variables that you're taking, which have chi-square distribution, their degrees of freedom, the second one has to have more than 4 degrees of freedom. So F distribution, it's slightly skewed on the right. Again, we'll see how it looks. Shape depends on n greater than 0. I'll come to this point in a minute. So again, here what we're talking about are sample variances. So it's just 2 sample variances. Again, it looks very similar to what we just saw. right? X by m and y by n. So here you just have x square and sy square, and that has m minus 1, n minus 1 degrees of freedom, and with an f distribution. Again, here also up above a certain value. This should be capital F actually. Yeah. Okay. So that's that. And okay. So these three properties. So if there is a random variable, now we can also denote it with z if that makes it simpler, because don't get confused by the x that we are using here. But oops, sorry. So any random variable which is distributed, which has an f distribution with mn, then its inverse will also have an f distribution. It's just that the degrees of freedom are going to get interchanged, because this had a numerator denominator sort of a formula. And if so remember, there was a restriction on what n should be. N has to be greater than 4, but there was no restriction on m. So m could be just 1 also. So if that is the case, then the root of x, that actually has t distribution with n degrees of freedom. And the other way is also true, that if x is actually t distribution, then the square of it becomes this. So these two are actually just inverse of each other. But yeah, these are just some more corollaries, I should say. Yeah, that's that. Any questions so far? I know it's not super intuitive. I'm pretty sure these are relatively new things, but let me know if there's something I can clarify further.
No, ma'am. But I have a doubt in multivariate normal.
Yes. Okay.
At the time of lecture, matrix sigma was taken to be diagonal matrix
Huh. Okay. So everything
in
here
lessons.
is zero.
Uh,
Okay.
Yes, but it is not necessary that every time covariance should be or correlation should be zero. There
Yes.
must be some correlation between two variables.
True. 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 Yes, it's not necessary. It could be anything. So the important part here is that the diagonal here, that has to be some value, because these can't be zero. Variance cannot be zero. Covariance, it could be zero also. So yes, so all of these values could be zero. They don't need to be zero. We'll take some very few examples, which might tell you how this would behave. But yes, you're right. It doesn't have to be necessarily zero. Okay. So Um, what am I saying here? So I think this we've already seen. Yeah. So yes, so it's just that these four things are what you have to remember as per their the symbols. Mean and variance of the population. Now, ideally, this is not known, right? Unless it's given explicitly. But sample mean and sample variance is known. So, for example, for your random variable um, x, which has a normal distribution, then if you want to find out about the sample mean and the sample variance, then these are the two things you can do. So the sample mean is going to be a normal distribution. The only thing is now, so the mean and variance, sorry, sample mean and population mean are going to, it's going to look like that. But the mean here will have, so again, it's coming from that formula. Wait, give me 1 second. Like, these are just different ways of writing what something that you've already seen.
Uh, it is a central limit theorem, distribution of sample
Yes.
mean.
Yes. So it's, and yes, absolutely correct. So it's also like suppose y is equal to ax plus b, and in this case, a is basically your 1 by n, right? So variance of y is actually a square variance of x, right? So variance of, variance y is equal to a square is mainly n square. Variance of y is sigma square. Why is this? Yeah, and also you're summing it up. So it should have, yeah,
N in the numerator and one n in the denominator will get
yes,
cancelled.
yes,
The
yes.
term will remain
Correct,
sigma
correct.
square by n.
Yes, perfect. Yes, good. So yes, that's what you get here. And then for the sample and population variances, this is something we just saw a few slides back. This is how they are related. So one in terms of normal distribution, one in terms of chi-square distribution. Again, we'll see few examples for some of these cases, so that will become slightly clearer. And so there's something called convergence of random variables. There are different things. The other things would be discussed in the next week. So in terms of probability, so again, this is very mathematical notation of something that you already understand. So suppose I want to say that my random variable has to approach a value x. Okay. So if I want to say that two things are equal or two things are almost equal, the difference between them has to be zero. Okay. Or the difference between them has to be almost zero. So if these two numbers are very close, if these two values are very close to each other, and so the absolute symbol here, the modulus, we're taking without the sign, that's just to ensure if you've taken, instead of 2, if you're taking 1.9 or you're taking 2.1, that shouldn't matter. The direction should not matter. So if the difference between the two numbers is a small value, so epsilon is always in maths, it's always used to refer to a very small value. And generally epsilon is taken positive because you're taking like an absolute number here. So the probability that this difference is a bigger number. So this symbol is mainly telling us that the difference is larger than a small number. We don't want that to happen, right? We don't want such a case to happen. Instead, what we want is that this difference should actually be really small. It should be smaller than epsilon also. So if you want this thing to happen, you want the probability of this to be as close to 1 and the probability of this to be as close to 0. So the difference, the modulus of the difference greater than epsilon, the probability of that approaches 0 as n approaches infinity, as you're taking more and more numbers, and the other way around. Now, what you can do is you can replace x with mu, right? So what happens here is this is going to become in terms of your sample mean, right? This becomes your sample mean. Sample mean approaches population mean. So ideally, when you want to estimate the population mean based on the sample mean, you would ideally need infinite values, right? We're saying this is infinite values, but we can't have infinite values. You can only observe finite values. So what becomes here? So another thing that people have seen here is, so when for epsilon greater than 0, and delta is another small value. So just like epsilon is a small value that we are using to compare the difference here, just like that, delta is another small value that we are using to estimate the probability. So the probability we want to be as close to 1 as possible. So 1 minus a very small value, right? So we want this to happen. This is what we want. The difference is a very small value. The probability of this happening should be a value as close to 1 as possible. For these two things to be true, for epsilon, a small number, and delta, also another small number, you would want that n has to be in this ratio. So it's sigma square divided by epsilon delta square. Now, what this means is, if you want your sample mean to be a good estimate of the population mean, so this probability has to be 1. That means delta is a very small value, right? Epsilon, anyway, epsilon small value, delta small value. Now, both of these would mean, so n has to be bigger than this formula. So n will have to be a very big number. So if you can have n as a big number, great. If not, then you would have to have delta not being a very small number. So that's just how it is. So you cannot have delta to be super small and also not have a lot of n's. Right? So something you might have heard in this context or different contexts is that you would want to have a larger sample size. Okay, you cannot just say something based on 3 samples or 5 samples. If you have more samples, then you get more confidence. So this is where it's coming from. Because if n was not small, if n was not big, then it would mean that this delta is actually a bigger value. If this delta is a bigger value, then you can say this probability is not very close to 1. So then it can mean that these two numbers are not good estimates of each other. All right. So far, so good. Okay. So before we go to the practice questions, let's go and solve a few things in R. Again, let me know if anything needs to be repeated. Okay. Give me 1 second. All right. So remember how there were these 4 formulas that we have been talking about for the past 2 weeks? Something to do with the PMF or PDF, something to do with the CDF, something to do with the quantiles, and something to do with the random number generator, right? So again, I have mostly copied all of these things from the previous script, so you won't. So there's a lot of things going wrong here, but anyway, so for the multivariate normal distribution, it does not come directly with the base R package that you get when you just install R. So you will have to install a package which is called the MVT norm, multivariate norm. That's the name. So when you want to install something, it's going to download the package first and then do the installation. So yes, you need the internet, but that needs to be done just once. And then every time you're opening an R session where you want to use this function, or not this function, when you want to use any function that comes with this package, then you will have to call the library for this package. Okay. So I don't need to do this step now because I've already done this. But I can just do the library step. If I don't do the library step, actually, so it will work because I actually have it loaded. I think I did that. So in RStudio, you can also, you have this graphic user interface. So you don't necessarily need to type the whole thing, but I'll just show you what I mean. And these are arranged alphabetically. So MVT. So you see something is already here. Oops. Yeah. Yeah. So this is already here and you see there is a tick here. So so forget what is written here, but now this is how it would be in your computers right now once you've installed MVT. Now, if I just run any function here, it's going to say, could not find the function DMV norm. Okay. So, but now what I do, if I load this library, if I load this package, then what you will see here, you will actually see that this tick comes up here. So I load this and you see that there's a tick coming up here when I loaded the library. You could also directly do it from here. It does the same thing. Okay. But yes, one of these two things has to be done. So Okay, now that we have called the library, so again this is not required. Okay, so now for the multivariate normal distribution. So right now we'll just talk about the bivariate thing. So what we have to do is, so we have to give it two sets of values, right? So when we want to give multiple values, multiple sets of values. So earlier when we were doing this, we just gave it a vector. Now what we'll do, we'll give it a matrix. And in that matrix, each column of the matrix is going to be our variables. For example, so remember we had seen this matrix functions. So when I run this, I'll just run this one separately here. So this is what it looks like. Okay, I have 10 numbers. I've said that distribute it into columns and fill it by row, like false. That's false. So it fills it by column. Okay, so that thing becomes your first variable and this thing becomes your second variable. So now I have two variables. Therefore, I need to give it two means also. Okay, again, this is, sorry. So this is what we're doing here. We've given it the values of x and y, and we have given it, we have to give it this mean, and we also have to give it another matrix. So this is, yeah. So we are giving it a mean, both the means. So since it's just two variables, we have to give it two means. Again, it could be anything. It doesn't necessarily have to be there. So again, two variables here, these are just values that the variables can accept, and you just want to see the distribution over these values. But the main nature of the graph is coming from these two parameters, the mean and the sigma. Okay, so mean is 1 and 3. So x has mean 1, y has mean 3. And now here, this is where one of you were asking, what sort of values do you want to give? Do you want to give an actual matrix? Do you want to give a diagonal matrix? So what's going to happen here is, so you have two options with you. Sorry. Okay, let me not write it like this. So it could be this, or it could be this. Okay. So now the important thing here is, so we are saying that the variance of x is 3 and the variance of y is 4 in both the cases. And in the other case, what we are saying is that the covariance is 1. And in the other case, we are saying that the covariance is 0. Okay. Now, again, this is based on what your data is. So both of these things are absolutely acceptable. It just depends on what sort of distribution are you looking at. So if that is done, then the formula, the command here is dmv norm. So we run this, and then what we get is so now you have 5 values, right? So here, so this was the first values, x and y, second value, third, fourth, and fifth. So corresponding to each pair of values, you have now got the corresponding value of the probability. Okay, yeah, not the probability, but the PMF, PDF, sorry. Yeah, this is going to be the, again, PDF here. So these things you can actually just ignore because, yeah, I think I've corrected this. This is fine. Okay. So yes, so the output is the PDF with as many, not with n elements. Yeah. Yeah. So output, this is, yes. Okay. So what I'm trying to say here is that, so P in this case, it's just 2, right? So number of columns is 2. So in this case also, it's making a diagonal matrix, and that's just 2 by 2 in this case also it's a square matrix 2 by 2 with diagonal elements telling you the variance. Mean also needs to have two elements here. So all of that is P. And the output depends on how many variables you gave it as the input. Another thing is, can you tell me line number 17? Is everything correct in line number 17 or is something wrong in that? So this command here, is everything okay? Do you think this is going to run without any error? So what you can see here is, here this matrix looks like this. Oops, sorry. So this is what, uh, sorry, this, yes. So this is what the matrix looks like, okay? Now, these two elements here, the non-diagonal elements, the 2, 1 and the 1, 2. So second row, first column and first row, second column. These values are different, but these values should not be different because these are just telling you covariances of X and Y, okay? So covariance of X and Y can't be two different values. It has to be a single value, right? So it does tell you that sigma has to be a symmetric matrix. So it's just that while you can give it any value, anything that you want, but it has to make sense. So this is one of the restrictions. So it has to be a square matrix and such it has to be a symmetric square matrix. Okay. All right. Now, again, if you want to see what these output values are actually telling us, ideally we would want a three-dimensional plot. But if we can't do that, we can still see what it looks like. So again, I'm just using the plot function, where the x-axis I'm referring to as this first column here, and y I'm saying whatever the output was. Okay, so just to make it simple, maybe I'll call this A. Let's call this A. Let's call this A actually. Okay. So what you can see here is, so this is the trend of your graph of the values of the PDF for values 1, 2, 3, 4, 5. So you can see that this does look like the descending arm of a normal distribution, right? So it's just, I mean, this visualization is in no way it is complete. You definitely have to have more values on the left, more values on the right to give you a better picture. But it does look like the end tail of the distribution. And yeah, this is also going to look the same because second set of values are the same that we are using here. Again, the one for CDF and the quantile, it works the same way. So I'm just skipping over that for now, but it will work the same way. When you want to do the random number generation, then it's it's the same thing. You have to give it, so now you don't have to give the X value, you just need to tell how many random values you want. So mean is, if you're saying that, okay, I need, so again, we're talking about a bivariate normal distribution. So that's the first mean, that's the second mean. And again, you can have your diagonal elements, so which are telling you the variances. So in this case, your covariance is 0. In this case, that's your covariance, or this is the covariance, or this is the covariance. So all of these, ideally, they should work. Let me actually write something else because 2 can be confusing. So this is what it looks like. Okay, that's your X and Y. So you've got 5 pairs of random numbers. This is giving you another 5 pair of random numbers. Now this thing here, this value, line number 32, it looks like it should be okay. But two values, two numbers, or two distributions which have 3 and 1 as the variances cannot have 10 as the covariance. So sigma is numerically not positive semi-definite. So again, there are some restrictions on the matrix itself. So it's not that you can just plug in any random value. It needs to be possible, but nevertheless, yeah. So these are just some examples. Okay, and of course, we can go above 2 also. The same thing, we can make a diagonal matrix with, so we can try this, for example. So let's say we have 3, like it's a trivariate distribution with, let's say, yeah, maybe these are our variances. This is what it's going to look like. Okay, x, y, and z, or x1, y2, x1, x2, x3, and so on. Okay. All right. Then again, chi-square distribution, same thing. The only thing now is for a certain set of values, you only need to provide the degrees of freedom. Okay. So you provide degrees of freedom, you will get as many outputs and you can plot that. So now here what you can see is that chi-square distribution, we saw that it is on the right side. Remember what we saw here for chi-square, that it's not symmetric and is greater than 0 and its shape depends on n. So we'll just see what that means. So if you don't want to plot it like that, the other thing is, we also saw this in a couple of classes back, you can directly use the curve function and it does the job. So what we can do is, let's actually take a few more examples. 4, 5, 6, and 7. Okay. So if I'm doing degrees of freedom 3 and I'm just saying curve, so by default, the curve function just plots between 0 and 1. So that's not enough. So we'll specify the x limit between 0 and 10. So we take a look at with degrees of freedom 1, that's what it looks like. Degree of freedom 2, it changes. Degree of freedom 3, it dramatically changes. Then 4 and 5, 6, 7, 8. Yeah. Oops, sorry. I think this should have been 3 actually. Yeah, like at 3, it actually changes. Okay. You can also increase it to 20 if you want to visualize it further. Right? So you can see it's shifting more and more. Then yeah, for chi-square again, CDF, same thing. Up to a certain value or above a certain value based on lower tail true and false with degrees of freedom. Then quantiles also. So if you want to have up to, like, so what is the value up to which your probability is 0.6. So 60%, the percentile. So 60 percentile of your values are up to what value, up to what number, then you can have chi-square. R chi-square, it's again for random number generator, right? So if you want to generate 30 random numbers which have 10 degrees of freedom, same thing for T distribution. Again, this should be PDF. So here as well, the formula here, so that was everything was CHISQ. For T distribution, it's just T. So DT, same thing. PT for the CDF, QT for the quantiles, and RT for the random number generator. Again, behaving exactly the same way. You just have to provide degrees of freedom. Now, T distribution can have negative values also. Okay. So like that. And right, remember this looks different from a normal distribution. Okay. Uh, did we say something here? Okay. Yeah. All right. And then we have the F distribution. Now for F distribution, the only thing is you have to give 2 degrees of freedom. So for the other two, we called it DF. Now for this one, it's going to be DF1 and DF2. Again, exactly the same thing. Uh, so the curve actually starts from 0, right? So everything before 0 is going to be 0. So it starts from here. Again, CDF, quantile, random number generator. That's that. So it's behaving exactly in the same way. So that's why I'm not um, explicitly mentioning everything, because we've discussed this already in 2 lectures. But of course, please let me know if you want me to detail any of this further. Just give me 1 second, okay? Yes, okay. All right. Um, at the in lecture 53, something more was discussed where you are making some functions. Now we will talk about this in one of the upcoming lectures, in one of the upcoming weeks. So, and since there is no question around this function, like writing a function in R in this week's assignment, so I'm not discussing it now because anyway, it's worth discussing when there's a full lecture devoted to this and when you have questions for this. So we'll definitely talk about this, but I don't remember if it's next week or the week after, but we will talk about this later. All right. And there's no question pertaining to this in this assignment. But now let's head on to what we do have in this week's assignment. Before we do the questions, do you have any other questions or any other doubt? Anything? If not, then so you have a few questions which look like this. Okay. Um, so if the PDF has this sort of a notation for X and Y random variables, you have to find the mean, the standard deviation, the value of expectation, and the value of variance. So would anybody like to tell how do we go about this? You don't need to give me the answers, but just let me know how you go about that. Nobody? Are we all tired? No problem. Okay. So what you want to do is you want to compare it with these formulas. I've just taken screenshots from the previous slides. So for example, again, I'm not exactly solving the whole thing, but yeah. So what you can do here is when you want to take the mean of X and Y, so you compare this thing here, right? So where did my pen? Okay. So if you compare this, then you can find that mu of X, that's 2, and mu of Y is 4, using these values, also these values here. And then when you want to compare standard deviation, so remember standard deviation, not variance. So standard deviation of X, that you can see the denominator. So you take the root of the denominator.
Ma'am,
Yes.
ma'am, your voice is little bit low. Little
My
bit.
voice is low. Okay. Let me just check my internet connection. My internet connection seems to be fine. Let me try again. Okay. So, oops. So yes, so when you have such a question, and you do have few questions like this in this assignment, so you want to compare, so you're given a formula, and you want to find values of mean and standard deviations of x and y and of the expectations. So when you do that, you just have to compare it with these formulas. So everything which is inside the bracket here, that becomes your mean. So mean of x is 2, mean of y is 4 here, as you can see in this thing. And then when you want to take the standard deviation, you can see that that's going to be 3 here. So because this is variance, that's sigma square. So when you want to find sigma, it's 3. And then the sigma of y, that's 5. Then when you want to find the value of the mean of, so expectation of the conditional probability, so that it's this term that you want to find. Okay, and this term here becomes your variance. So this term comes from here. So if you say 1, 2, and 3 and 4 things, then this is 1, this is actually 3, this is 2, and this is 4 here. So again, just calculate. So what you, in addition to that, so x would be given to you in the question. So this value of x and this y, so small x and small y would be given. In addition to that, so you have your mu y, you have mu x, you've got sigma x and y respectively. The only thing that you're left to solve is rho. So what we can do here is, we can just compare. We can say that 2, so you can take from here actually. So 2 rho divided by x sigma and sigma x and sigma y, that actually becomes 1 by 9 here. Okay, so 2 rho and sigma x sigma y is 3 and 5. That's 1 by, oops, 1 by 9. That gets cancelled into 3. So rho is actually equal to 5 divided by 6. Right? So it has to be solved like this. Again, this question exactly, you don't have to solve the whole thing, because this was just a random example. But, and of course, you can also solve this through this part right here. But again, this is how you have to solve those questions. So just comparing. Okay. Is my voice okay now? And were you able to understand how this was done?
Yes, ma'am.
Okay. All right. Great. Um, then yeah, so these are some way also questions that you have in your assignment this week. So if you are to calculate, if you're asked how do you calculate the probability, and you see these are very similar questions. Chi-square with a degree of freedom 15, less than equal to 25 or greater than 25 in R. So what's the formula that we're going to use? So again, remember there were these 4 types of formulas that we've been talking about. Okay. So for chi-square, for example, it's going to be this formula. Okay. P chi SQ. And instead of Q here, you're going to give this value. So it's 25 here. And then it says degree of freedom. So that's going to be 15 for this question. Okay. That's 15 here. And then lower tail. So when you have this sort of a notation less than 25, then you say lower tail is true. And when you're doing a greater than 25, then you do lower tail false. Similarly, for t distribution, it's again going to be the same way, absolutely the same way. For f distribution, you'll just have df1 and df2. So first for t distribution, and for f distribution is going to look like this. Okay, df like that. So these are the type of questions you can get in your assignment, or I should say the exam, and you would have options to choose from. So how do you calculate? So again, these are the answers. I can maybe copy this here, but the main question is how do you, the main question actually is how do you actually solve this rather than the answers. But yeah, this is the answer that you should get. Okay. Um, and yeah, it just, so also read the question carefully. So for example, if it's T with 16 and this is T 15, then these are like different values. Okay. All right. Now we have two questions actually here, which are slightly more numerical. So an experimenter is attempting to locate a target in three-dimensional space, and the three coordinate errors. So if you're trying to locate something, you can have errors in them. So, and the coordinate errors, which is in meters of the point chosen, are independent normally distributed random variables. They are independent normal random variables with mean 0 and standard deviation 3. So what's the probability that the distance between the point chosen and the target exceeds 4 meters? Okay. So let's do it step by step. Would anybody like to give it a try, or should I start solving it? Yeah. So the thing at the bottom, that was actually the hint. Um, but yeah. So before actually the hint, there's one important thing that we need to know, which is about the distance. Okay. So the question we start off is, what is the probability that the distance, which is between the point and the target, that exceeds 4 meters? And just make sure that this is also meters and this is also meters. So we are talking about the same unit. Now, there's one, have you heard about this term, Euclidean distance? So whenever we are talking about 2 points, which are in 3D space, when you're talking about X, Y, and Z. So whenever you're doing that, if we are saying that the distance between them is D, then what we are actually saying is, so you can have this projected in 3 dimensions, right? So for example, if you're just talking about 2 dimensions and you make this line here, then you can actually project this on the y-axis and you can project this on the x-axis, right? So if this was A and if this was B, then that's basically C, right? And you know, this is A square plus B square is equal to C square. Likewise, for 3D also, it holds the same formula. So D square is actually equals to X square plus Y square plus Z square. So you can say Euclidean distance, or you can say the three-dimensional variants of Pythagoras theorem. Okay. So this is another formula that you have to, that we are using in this formula, in this question. Okay. So what we can do is, if you want to convert, we want something to do in similar thing. So what you can do is, we'll just square up both the sides. We'll say D square has to be greater than 16. And now, instead of D square, we can write X square plus Y square plus Z square. That has to be greater than 16. Is this making sense until now?
Yes, ma'am.
Okay. Now, the other thing is, so when we're talking about normal distribution here, the normal distribution thing here, there's another factor here, which is this mu and sigma square. Now, mu is 0 here. Where did it go? So mean is 0 here, but sigma is actually 3. Okay. So what we can do here is, so the sum of the standard normal variable is going to follow chi-square distribution. So that means that x minus 0 by 3 whole square plus y minus 0 by 3 whole square plus z minus 0 by 3 whole square. This follows chi-square distribution with 3 degrees of freedom, because we're talking about 3 random variables, 1, 2, 3. So this mainly means that x square plus y square plus z square by 9, this follows chi-square distribution. So now this, what we can do is we can say probability of x square plus y square plus z square. Let's divide by 9 also, both sides. That's 16 by 9. So now what we just need to find out is the probability of a standard normal, probability of a chi-square distributed random variable has to be greater than 16 by 9 with degrees of freedom. So n is 3. Degrees of freedom is 3 here. And now that we can do using R. Okay. So, yes. So for example, here, again, we can just use the p chi-square formula, and then we want to find that the value has to be greater than 16 by 9. So we'll just write 16 by 9. And degree of freedom, that was 3 in this question. And then we want to find it greater than that, greater than this value. So we'll say lower tail is false. And that value that we get is 0.62. So that's your answer here. Oops. Okay. You could also do it. You could do lower tail true and then do 1 minus lower tail true. So that does the same thing. Okay. So that's how we can do this question. So you do have a few questions like this, I think. And a very similarly designed question. Again, it uses a little, it's a different distribution, but it's on similar lines where you have to identify what distribution are we going to talk about. So in this case, we are saying that the time it takes to fill a medicine bottle is normally distributed with, oops, sorry. Okay. So the time it takes to fill a medicine bottle, so that's normally distributed. So it's a normal distribution with mean equal to 10 and standard deviation equal to 3. So you can say it's 9. So mean is 10 and standard deviation is 3. So variance is 9. If a sample of 20 such jobs is to fill the bottle is observed, what is the probability that the sample variance will exceed 12? So sample and sample variance. So now the probability that the sample variance is going to exceed 12. That's the question. Oh, sample variance. So it's going to be S square. So any ideas which one are we going to use here? Remember there was one relation where we were comparing sample means, sample variance and population variance.
Ma'am, cascade distribution is used.
Yes, perfect. So this one with n minus 1 degree of freedom. So in this case, n is 20. So the degree of freedom that we'll talk about is going to be 19. Okay, here. So you want to have it in this version. sorry, in this notation. So what we can do is, again, we'll just divide both the sides by sigma square. So s square by sigma square, that's going to be greater than 12 divided by 9 here. Okay. And then we can also have the n-1 term. So n-1 s square by sigma square. So n-1 is 19 here. So that's going to be 19 into 12 by 9, right? So now we just have to find out. So this term, so of course we can simplify this. So probability that this chi-square n-1, this is greater than 76 by 3, right? So again, we do the same thing. So chi-square, so again, it's going to be p chi sq. This was 76 by 3. Degree of freedom has to be 19 this time. And again, we want greater than. So lower tail will be false. And now we've got 0.15. Okay. Cool. So I think that is all. Yep. That's it. All right. Cool. So yes, so we talked about the multivariate, or rather the bivariate normal distribution. We talked about chi-square, t, and f distributions. We introduced something called the statistic, or something called the sampling distributions, which we will explore more in the next upcoming weeks. And we'll also do a little bit more R, where we are going to define some functions. Like we'll make some functions on our own. And yes. So the deadline for this week's assignment is day after tomorrow, Wednesday. And I'll upload the recording and the slide and the R script on YouTube and Google Drive respectively. And if there are no more questions, then I'll meet you next Monday. All right. So thank you everybody for joining. And if you've missed something, then you can take a look at the recording, which I will upload in a little while to the YouTube channel, and you'll have the link through the course page. All right. Okay. Thank you so much. Good night, everybody. Bye-bye. Thanks for joining.